Welcome back, Math 30. Today we are going to look at rational functions and their asymptotes. Okay? So to start off, what is a rational function? Well, in a rational function, we have two functions kind of put together, one being the numerator and one being the denominator. So let's put two functions as a fraction. All right? Now the key thing here is your denominator function cannot have a degree of 0, because anything to the degree of 0 or to the power of 0 is 1. And if it is to the degree of 0, well then it's most likely just a polynomial function. It's just our numerator function over 1, which is going to be a polynomial. So here are some examples of rational functions. If we look at this, we have the top here, degree of 1, and our denominator function is a degree of 1. The second one here, we have our numerator function, degree of 0, because it's equal to 1. Well, it's okay if we have our numerator function with a degree of 0, we just cannot have our denominator function with a degree of 0. And this one here, my denominator function, is a degree of 2. This one right here, we have numerator function, a degree of 2, and denominator function, a degree of 1. Alright? Asymptotes, or our points of discontinuity. The non-permissible value is when our denominator is equal to 0. Why? Because we can never divide anything by 0. Now, one type of discontinuity is called an infinite discontinuity. This is the most time leading to a vertical asymptote or something like that. Another point of discontinuity would be a hole. And we're going to look at that a bit later. Okay? So the first one, so for infinite discontinuity, you'll end up seeing graphs that kind of look like this. Okay? So we have an asymptote over here that's infinitely discontinuous. Our second one is a hole in the graph. So that would be something like this. Oh, and then there's a little hole, and it keeps on going. Okay? Now, we're going to figure out how to calculate these throughout this lesson and how to find them by just looking at the graph. So here is my first equation that we're going to look at and discover. It says, since division by 0 is not defined, the non-permissible value of this function is, well, we know the denominator, x minus 1, cannot equal to 0, so then x cannot equal to 1. So my non-permissible value is 1. Okay? Now it wants us to complete this table here and plot the points on the graph. So if I put in negative 5 for x, I'm going to have negative 5 minus 1, which is negative 6. So that's 1 over negative 6. Then we look at negative 2. That's going to be 1 over negative 2 minus 1 is negative 3. Then we have 1 over negative 2, 1 over negative 1, and then this one here, 1 subtract 1 is 0. 1 divided by 0, well, that's my non-permissible value. So there's absolutely nothing that we could put there. Next one, we're going to look at 2. 2 minus 1 is 1, so that's 1 over 1. Okay? Then, here, we're going to have 3. 3 minus 1 is going to be 2, so that's 1 over 2. Here we're going to have 1 over 3, and then 1 over 4. Alright? Now this one here, and this one here, this is the same as negative 1, and this is the same as 1. Okay? So let's start plugging this in, see where we go. So when we're at negative 5, when x is negative 5, my y value, this is the same as y, is going to be 1, 6. So that's very close to 0, so I'm going to put a dot there. Next one is negative 2. Negative 2 is right here, we're at 1/3. And then 1/2. And then we're at 1, it says. And that's 0. So it looks something like that. Now, we have nothing there. Then at 2, so we'll go over. At 2, we're going to have 1. So 2 is at 1. Then we're going to look at, we have 1/2. Then we're at 1/3. Then it's at 1/4. And it keeps on going down like that. Alright? Now, it wants us to fill out these points now. If we notice, these points here are getting very close to my non-permissible value, 0.5. It's closer. So 0.5, if I put in 0.5 for x, that's 1 all over. 0.5 minus 1, well, that's going to be negative 0.5. So that's 1 over negative 0.5 is negative 2. Next one here is 0.9. So 0.9 minus 1 is going to be 1 over 0.1, negative, which is the same as negative 10. So this one here is negative 10. The next one, if we put that in for x, we're going to get negative 100. Then if we put 1, well, there's nothing there. Put in this here, this is going to be positive 100. 1.01 minus 1 is 1 divided by 0.01, which is 100. Then we're going to get 10. Then here we're going to get 2. So let's start plugging these in. So negative 2. So when I'm at 0.5, which is around right there, I'm going to be at negative 2. When I'm at 0.9, which is right there, I'm going to be at negative 10, which is somewhere around there. Okay? Now, when I'm at 0.99, which is like right on the line, I'm at negative 100, which is way down here, so it just keeps on going down. I'm getting close to it. Now let's take a look at 1.01. If I'm at 1.01, I'm at 100. I cannot find that. Let's take a look at 1.1. 1.1 is around right there, and that's going to be positive 10. So it's right around there. Okay? Next one is going to be at 1.5 is 2. So 1.5 is 2. Now, I look at this, I have a graph I can make. So we're just going to look like this. And it's going to continue and go all the way down like that. And they go forever. And this one's going to look like this. It's going to continue and come across and go all the way like that forever. Alright? Okay, let's take a look at the next part here. It says, using a graphing calculator, check. So, graph this equation in your calculator. So I grab my calculator, and I'm going to go 1 divided by bracket, and we have x minus 1. So we put in x subtract 1. I want all of this divided by x subtract 1, that's why I put in my graph, or my brackets, now I graph it, and it looks like that. Well, if I want to narrow it in a bit, I'm going to go, that's fairly high, I'm going to go 10, 10, just change my numbers a bit better, and there's my graph. So it's very similar to what we kind of drew there. Now it says, describe what happens to the value of the function as x gets more positive. So as x gets more positive, what happens? So as we go farther that way, we approach 0. Okay? So as x approaches infinity, as it gets infinitely bigger, we approach 0 from the positive. Y approaches 0 from the positive. So y decreases kind of until we hit 0. It gets as close to 0 as possible, decreasing but never hits. Now describe what happens to the value of x as we get more negative, as we go this way. So this one, as x approaches negative infinity, what happened? Y approaches 0. But this one is from the negative. So it's approaching 0 from the negative. Okay? So from the negative. So this one is constantly increasing and approaching 0. So it's constantly increasing and approaching 0. And it's from negative, so it is increasing. This one here is decreasing. But they get closer to 0, but they will never touch. Now it says, from the equation below in brackets, circle the correct alternative for each statement below. As x gets closer to the non-permissible value, the value of 1, from the left, the function approaches what? So we're going from the left. So from the left, as x gets closer, we get more negative. We get to infinitely negative my y value, right? Now it says, as x gets closer to non-permissible value 1 from the right, so from the right, we go infinitely increasing. It goes infinitely up. So this one is going to be that. Okay? So now let's review what we learned about asymptotes there. So in this question here, we had a vertical asymptote right here. Okay? My vertical asymptote was the non-permissible value. Okay? We also had a horizontal asymptote at x is equal to 0. And that's kind of what it says here. The vertical asymptote is at my non-permissible value. My horizontal asymptote was at 0. Now the reason why this one has a horizontal asymptote, we'll discover a little bit later. If I look at this, what is my degree on top? And what is my degree on bottom? The degree on the bottom is bigger than the degree on top. Therefore, my asymptote will be 0. Now let's take a look at my next one here. It says, consider the following function. We have 3 over x. State the domain of the function. Well, I look at this. What can x not equal? X cannot equal to 0. And x is an element of all real numbers. Okay? So that is my domain. Okay? Now it says, using a graphic calculator, graph, but do not sketch. So let's see what this looks like. I'm going to clear this and put in 3 divided by x, and enter. I'm going to graph it. I get something that looks like that. So, write the equation of the vertical asymptote. Well, my vertical asymptote is going to be when x equals 0. Okay? Now let's just show the vertical asymptote on the graph. So we're going to show it. It's right here. Okay? Now complete the graph on the grid. So my graph is going to look something like this, because we know my asymptotes, there, and there. Because my asymptotes, I have a horizontal at 0 and a vertical at 0. So y is equal to 0 is 1, that's my horizontal, and x is equal to 0 is my vertical. All right? Because my degree is bigger on my denominator than my numerator. So now it says state the horizontal, that y is equal to 0. State the range of the function. Well, y is an element of all real numbers, but y cannot equal to 0. So we're looking at y such that. So it's going to look like that there. Now let's take a look at my next one. It says, analyze this one here. If we notice this one now, we have the same degree. Degree of 1, degree of 2. So state the domain of this function. Well, in this function here, x cannot equal to -1. And x is an element of all real numbers. Okay? Now it says, using the graphic calculator, sketch this. So I'm going to put in 2x, right? And we're going to divide that all by x plus 1. Graph. So this is a bit different. Look where my horizontal asymptote is. Now, use the graphic calculator sketch, write the equation of the vertical asymptote. The vertical asymptote is still at x is equal to -1. So let's draw that in. -1, we have my vertical asymptote. Okay? Now, it wants us to estimate the horizontal asymptote using the table function. So I'm going to go right here. We're going to go to the table. And I want to find my vertical. So let's keep on going down. If I'm in the 50s, 100s, if we look at this, we're just getting closer to 2. But we're never quite reaching 2, are we? I go up, and we're just never getting close to 2. So it's getting infinitely close to 2, so it's not. So based on this, it is going to be y cannot equal to 2. Now complete the graph for a dashed line for that one. So it's at 2. And if I put my graph, it looks about right, because right there's 2, and it looks like it never quite reaches 2, gets infinitely close, but never quite reaches. Now we want to complete the sketch of the graph. My sketch looks something like this. Okay? Now state the range of the function. Well, my range, we're looking at y, and we know that y cannot equal to 2. And y is an element of all real numbers. So that's it. Okay? Now, if I look at this, what's the key? What's the leading coefficient for the numerator? Leading coefficient for the numerator is 2. The denominator is 1. So that's 2 over 1. That, you might see, can help you find the horizontal, when the degrees are the same, the horizontal asymptote. Okay? Let's take a look at the next one here. We have x squared all over x minus 2. Let's try it out. So we want x squared. So we have x squared all divided by, we have x minus 2. Okay? So my graph looks something like this. I'm going to make it bigger so we can see it more. It's a lot bigger now. Now we can see it all. So it looks something like that. Alright, so draw the vertical asymptote. Well, we know the vertical asymptote, again, is x cannot equal to 2. Alright, so let's draw that vertical asymptote right here, because we cannot divide by 0. Now it says, use the graphing calculator to sketch the function. So let's go right here. I look at this. I'm going to go back to 10, zoom 6, So just we get a little glimpse. So I have 0 there, and this part here, this minimum, is going to be at 8. You could do it by calculating your min in your graphic calculator. So we have at 8 something that looks like this. And then we're going to have at 0 something that looks like this. Okay? And it touches. Now, I look at this and it says, does this formula have a horizontal asymptote? Well, I have a huge gap there, don't I? So, no, it does not. Okay? Use the feature of the to determine the domain and range. Okay? So, to determine the domain and range, we could find our max and min. So I'm going to go second calculate. I'm going to find my minimum. So I'm just going to go over. So I go there, left bound, enter, right bound, enter, and then my guess, enter. Right there, I get a minimum of 8. So y must be greater than 8, and let's find my maximum for this one. So we go over, left bound, right bound, and there's my guess. I get 0, my maximum is 0, and y must be less than 0. And y is an element of all real numbers. So that is my range. Okay? Or equal to, sorry, it could also be equal to, that's my mistake. Must be greater than or equal to 8 or less than or equal to 0. Right, so if we look at this, if the degree of the numerator is bigger than the degree of the denominator, then we end up having no horizontal asymptote. Alright? So now I suggest you read over this part here to give you a little bit more information. So now just as a review, vertical asymptotes are always our non-permissible value. We just get the denominator function to be equal to 0, and that gives us my non-permissible value. My horizontal asymptote is, well, it depends on the equation. Alright? If my denominator is a bigger degree than my numerator, then it's going to be 0. The horizontal is going to be at y is equal to 0. Alright? If my degree are equal, I take my leading coefficient of my denominator, or of my numerator, and I divide that by the leading coefficient of my numerator. And that will give me my horizontal asymptote. So this one will be 2 over 1. Okay? If the degree of the numerator is bigger than the degree of the denominator, then we have no horizontal asymptote. Okay? There's no horizontal asymptote. Now, let's take a look at this last example. Algebraically determine the equation of the asymptotes of this function. So I look at this, it's the same degree. If it's the same degree, I kind of already know my horizontal. Alright? So, let's take a look at this here. I'm going to start factoring each one. This here can be factored to x plus 3, x minus 2. All over, now we're going to end up getting 2x if I factor it, plus 3, minus 3. And we're going to have x plus 1. Alright? Now based off this, I could tell my vertical asymptote are, well, this is equal to 0, so we have 2x minus 3 cannot equal to 0, so then we have x cannot equal to 3 over 2, and we have also x plus 1 cannot equal to 0, so x cannot equal to negative 1. R, so we have x, r, 3 over 2, x equals to 3 over 2, and negative 1. Okay, so that's it. Well, good luck. See you tomorrow as we work on this together.